Okay, sorry the video cut off. The cat was walking on the keyboard. Okay, so we left off reviewing isotope notation. Okay, so I want you to tell me which answer here is correct, A, B, or C, and show your work as to how you calculated the number of neutrons. Okay, this is the same question. All right, we talked about this slide in class. The bottom line here is that when the protons and neutrons are equal, this is stable, which is another way of saying not radioactive. When the number of protons is way smaller than the number of neutrons, we use the example of lead 210 in class. That's very unstable, and it's going to try to get rid of some neutrons, essentially, okay? You might also have a situation, it's a little more rare, but you might have a situation where, so this is where you have like lots of neutrons and very few protons. So that's what we call beta decay. That's when it's trying to kind of get rid of a neutron. Or create more neutrons, actually, is what it's going to do. On the other hand, when you have a lot of protons, so our atomic number is high, but we have a relatively low number of neutrons, then you're going to end up with positron emission or something we call electron capture. All right, but if we're on this red line where it's protons and neutrons are equal, then no big deal. It's stable. No radioactive decay happens. Okay. We also spoke about half-life, so I'm going to skip ahead to this example. I did this for you in class. You can feel free to skip this in the video if you remember it, but I thought it would be a good idea to review since this is not in your textbook. The half-life of iodine 131 is 8 days. So how much iodine 131 would be left if we start with 32 grams and when we go for 5 half-lives? So this is called the bucket method of calculating half-life questions. It's a really good way of doing it for kind of an introductory chemistry approach. We don't need to use any logarithms or anything complicated. But basically, and each bucket represents the mass that we have. The first bucket has the mass initially, and of course the last bucket's going to have what we have at the end. Each time we transfer from one bucket to another, it represents a half-life. That means that half of the stuff has decayed. So 32, half of that, in other words, dividing by 16. Sorry, 32 divided by 2 is going to give us 16 grams after one half-life. So each arrow, so an arrow means half-life. So in other words, what we're communicating with this diagram is I start off with 32 grams, 8 days passes, and I have 16 grams. 8 more days pass, and it's going to be 16 divided by 2. So in each box, we're in between them, we're dividing by 2. 16 divided by 2 is 8 grams. After 8 more days, now I've got 4 grams. We keep doing that. It says 5 half-lives, so I got to have 5 arrows. I got 1, 2, 3, 4. After 4 half-lives, we have 2 grams. I don't know why it just disappeared. And then after the 5th half-life, we have just 1 gram left. So the answer to the question is that if 5 half-lives have passed, we have 1 gram remaining. You can also figure out that based on 8 days for every half-life, right? If we have a statement where it's half-life equals 8 days, we can turn that into a fraction. 8 days for every half-life. So we can figure out how long it has been because we know that there were 5 half-lives. That's an L. So the half-lives are canceling here, so 8 times 5 gives us 40 days. So if we started with 32 grams of I-131, in 40 days we would only have 1 gram of I-131 left. The rest of it is been converted to something else, to some other element. It's no longer iodine anymore. Okay, we're skipping this one. I don't like it. Okay. We did this one in class, so I'm not gonna ask you these two again. You already did this, so I'll skip ahead a little bit. So as we discussed, there's 3 types of radiation: alpha, beta, and gamma particles. And so my question here for you is, do you remember which one is heavier? Also, which one is positively charged, which one is negative, and which one is neutral? So fill these in as a review. Try not to go back in your notes and look. See if you remember. Okay, so here's some more info about alpha particles. Alpha particles are 2 protons and 2 neutrons, which means they have a mass of, so it's protons plus neutrons, they have a mass of 4. The atomic, oops, I put that in the wrong spot. The atomic number is going to be just the number of protons. So there's 2 protons. And so the atomic number of the element number 2 is helium, as I said before. So helium with a mass of 4 is an alpha particle. So we can write that in 2 ways. You can write that as the alpha symbol, which is easier to write, but doesn't really help us when we're trying to figure out how to balance these reactions. Or we can write it as helium over here with 2 protons and a mass of 4. Most people prefer to do it this way because when you do, you can figure out what your other component is going to be. So for example, a kind of question we're going to get for this chapter is the alpha decay of uranium-238 can be written in 2 ways. All right, so the question would be, write the decay of uranium-238. So decay means that it's producing this. It's producing alpha particles. So I'm going to start out by writing uranium-238 with the right isotopic notation that we learned. And then I know it's going to be an alpha particle, so I can either choose to write the alpha symbol or I can choose to write 4 helium with a 2 in the bottom. At that point, I don't know what the middle element is. This is a big question mark. I got to figure it out. It's easier to figure it out if you write it, the alpha particle, as a helium. Because essentially the right-hand side, the top numbers are going to add up and the bottom numbers are going to add up. Right? So 90 plus 92, oh man, I just did the math and skipped ahead. 90 plus 2 gives us 92 on the left-hand side, and 4 plus 234 gives us 238. So these reactions are balanced. They have the same numbers of protons and neutrons at the end as they did in the beginning. So we can use the helium notation rather than the alpha particle symbol to help us balance the reactions easier. All right. And then of course, once I know that there's 90 protons, I have to look on the periodic table and find thorium. So that's our process. Okay. So this is showing the same idea in a bit more detail. All right. So what we call this is balancing the mass, which is the top numbers, the red, and balancing the charge. We want to make sure that the protons are equal in the beginning and the end. So here's a real story. In 2006, a Russian FSB, that's the spies for the Russian countries. The Russian countries' spies are called FSB agents. And one of them, named Alexander Litvinenko, was poisoned with polonium-210, which is the element that Marie Curie discovered. Basically, somebody stuck it in the end of an umbrella, and when he was walking by them in a diner, they stabbed him with the umbrella. And kind of like injected a tiny amount of polonium-210, and he got radiation poisoning and died. So we're beginning with polonium-210. We're going to write that as PO. Oh, by the way, some of these elements are pretty rare, so you may not know the symbols and stuff. Your book, at the end of the book, I think, maybe the beginning, has a list by alphabetical name of all the elements with their symbol. Okay, so if you don't know what polonium is, you can just look it up there, PO. I don't expect you to memorize those. Okay, the heavy metals are mostly the ones that are radioactive, and they're kind of rare. So use your textbook to help you find those. So polonium is PO, and it says 210. When this notation is used, that means that it has a mass of 210. In order to figure out the number that goes on the bottom, I got to look it up. So here we have my periodic table. It's a little snazzier than the one that we can print at school because, you know, it's color. So polonium is PO. Here's the name on this particular table. It says its atomic number is 84. Okay. So the key for this particular periodic table is up here. So I wasn't sure which number is atomic number, but they say the top one is. So we're going to use that. So the atomic number is 84. So we're going to write 84 down here. That's what we're beginning with. Okay, that's what they say that it's starting. Okay. Okay. So then it says it will decay by alpha decay. So decay, a decay reaction means that we have one reactant, polonium-210, and it's going to make at least two products. So like in this case, it says it's going to be alpha decay. So that means I have an alpha particle plus something else. Okay, so if I produce an alpha particle, that means that I start with a mass of 210 and I have to use 4 of those in my alpha particles. So I guess that my mass over here is going to have to be 210 minus 4, so 206. And then over here the protons work the same way, 84 protons to begin with, but I took 2 of them off, so now there's 82. And then we got to look at the periodic table again. Oops, I can't find it. Here we go. And we got to find out where element number 82 is. Oh, that's Pb. Oh, it makes lead. Well, lead poisoning sucks too, so even once this stuff decays, it's still poisonous. Not quite as poisonous, but still pretty gross. So, polonium-210 is pretty hard to detect, but we have lots of ways to detect lead, so probably, I'm guessing, after he was dead, when they did the autopsy, they would have tested his blood and his muscle tissue and found some lead residue there. Maybe a little polonium-210 as well. Okay, so the correct answer here is going to be letter C. All right, so now if we have beta particles involved, then what's interesting is they have the exact same mass and charge as a proton, right? So a proton has a mass of 1. And so basically what happens is a neutron is decomposing. A decomposing is another way of saying decay. So we're starting off with a neutron, and it produces, that's the arrow, an electron. Okay, so if we have a neutral neutron and we take away a negative charge, that's going to leave a positive charge behind, which is a proton. Okay, so this is kind of weird. So what's happening is a neutron, we have too many neutrons when we do beta decay. It kicks out an electron from the nucleus. They can't be in the nucleus, okay, so that leaves really, really fast. Protons belong in the nucleus, so in effect what we're doing is increasing the atomic number of our nucleus. Okay, the mass is the same because we started with a mass of 1 and we're ending with a mass of 1, and electrons don't weigh anything really. So when we kick that out, we don't lose any mass, but it does increase the atomic number. All right, so when we write the symbol for beta particles, we use E because of electrons. It has to say -1 because otherwise they won't add up correctly. Like, all right, so if we have 6 protons to begin with, and one of the neutrons in there decays by releasing an electron, it's going to leave a new proton behind. So now I have 7 protons. Well, the element with 7 protons is nitrogen. So we went from having carbon to nitrogen in this process. All right, and so like on the right-hand side, it's -1 plus 7 to get 6 protons. So that's going to match the number that we started with. The mass is exactly the same, which is actually more stable. Carbon-14 is very rare and radioactive, and it decays by releasing an electron called beta decay. But that means the mass stays the same because electrons don't have weight. The most common isotope of nitrogen is 14 AMU because its mass is 14.01 on the periodic table, right? So that means this is a very stable process. Once you get to the nitrogen, it's really stable. You can also use the symbol beta. That again is a little bit more tough for people to balance because you got to remember it's -1 proton here when you emit a beta particle. Okay, so I want you to try to write the reaction for cerium, which is Ce. That's the symbol 144. So start off by writing your decay reaction, very similar to what we did for alpha decay, except this is a beta particle. And then tell me what other product besides the beta particle we are going to get. And I'll check that when I look at your notes. Finally, we have the easiest one of them all, gamma rays. Gamma rays are just energy. They don't have any mass. They don't change the atomic number. It's just the nucleus's way of releasing energy. All right, and so they're easy to write reactions for. There's only one symbol, the gamma, so you got to practice writing it kind of a little bit. It's fun. But when we have boron with a mass of 11, it emits gamma particles. That's radiation. It doesn't change anything about the boron, except now the boron is not as high energy as it used to be. But it's still boron with the same mass because gamma particles don't have mass. Okay. Typically, gamma particles get emitted at the same time as other substances. So example of that is polonium-210. We said it emitted alpha particles earlier, and so if it has a weight of 210 and it gives up 4 of that, we're going to have 206 left again. And of course, 84 minus 2 is 82. So that's still lead, right? That's the reaction that we got from the last slide. Not the last one, but a few slides ago. In reality, that's not the whole story, though. It's not just emitting an alpha particle. It has so much energy that when it emits the alpha particle, it also emits a gamma particle, gamma ray, we call it. Okay, so it's really a high energy radioactive decay process. You get the alpha particle, which is lots and lots of energy, does a lot of damage to living tissues, and you get the gamma particle, which is even higher energy. Okay, so it seems like radiation is pretty dangerous, and it can be if you're not cautious, appropriately cautious. In fact, Marie Curie and Pierre Curie's lab was well known for not being very safe. Okay, so it's not all a good thing back then, but now we know that alpha particles are easy to block since they're pretty heavy. Remember that they're the helium with a mass of 4, so that's the biggest kind of radioactive particle. You can block it just by putting a piece of paper up, or okay, so you can just use a piece of paper to block alpha particles. Also, your skin will do the same thing. Your skin is thick enough to resist alpha radiation. Beta particles are a little bit lighter, so they can actually travel right through the paper. That means that we need something a little thicker, a little more dense in order to block it. So lead, 1/2 centimeter of lead. 1/2 centimeter is not very much. It's basically just a lead sheet, okay? It would still be kind of like flexible, right? So your pinky is about 1 centimeter wide, so 1/2 centimeter is half as wide. That'll stop beta radiation pretty well. Gamma radiation is so light, it has no mass, it's just energy, and really, really high in energy too. So it goes right through the paper, it goes right through 1/2 centimeter of lead. And as it turns out, you need a lot of lead to block that. 10 centimeters of lead. Okay, that's a roughly, 2.5 inches, I think. So a pretty thick chunk of lead to block that. Okay. So like when you go to the X-ray technician and you get an X-ray, they put a vest on with lead in it. It's got about a 1/2 centimeter sheet of lead sewn in between the fabric. And that is because X-rays can be blocked by the lead just as well as beta particles can. And that protects like your organs, which are more damaged by radiation than, your arms. So the question here, penetrates means which, like, goes through the most, right? Which type of radiation goes through the most amount of matter? And the answer there, of course, is gamma particles. The least penetrating radiation is alpha. Okay. All right. So we're going to practice the bucket method again. All right. If I start with 1 gram of material, oops, too high. Let me try that again. So 1 gram of material, and it took an hour to reduce that by half, then the half-life is 1 hour. Okay, so again, we're using arrows to represent a half-life. The buckets are just how much stuff I have after each step. All right, so carbon-14 has a half-life that's really long, 5,730 years. So if I started with 1 gram, and I went 3 half-lives, not 1 hour here, that's 5,730. I went 3 half-lives, so right now I got 1 there, here's 2. 0.5 divided by 2 is going to give me 0.25. And then 1 more half-life, 0.25 divided by 2 is going to say 0.125, but I don't have room, so I'm just going to write 0.13. So 3 half-lives, you got 1, 2, 3 arrows, 3 half-lives. We would have 0.125 or 0.13 grams left over. So that's how we can answer this question. Of course, we can also, again, figure out how many years, in this case, have passed by just using dimensional analysis here. We have 3 half-lives, so that cancels the half-life, and we get the fact